Hi, I'm Franz. I lead design at Tesla.
And I'm Lars. I've been doing vehicles with Franz for almost 13 years now.
So I joined Tesla in 2008 to vertically integrate design into the company. It didn't exist before. It was a pretty small team. It was tasked with designing the most beautiful, innovative, and well-engineered vehicles on the planet. No small task in 2008. There was not a lot going on in the EV sector then. Since then, we focused on constant improvement in cost, efficiency, innovation, things that you'll continue to hear about today, while continuing to design the most desirable cars. Today, we produce cars differently than we did 10 years ago. But the end result is always an exciting, futuristic, and desirable set of vehicles.
Back then, we only had a handful of designers and engineers like myself, but we had a great vision to radically change transportation.
So back in 2008, where we were designing Model S, we didn't have a factory. In fact, we had a really small engineering team and a tiny design team. But that allowed design to lead all the conversations. It let us innovate forward-thinking ideas, like how do you fit 7 people into a sedan? Or how do you make door handles disappear into the doors? Or putting a huge touchscreen into the center of the vehicle, something that had never been done before.
And then we won Motor Trend Car of the Year.
Yes, and we won Motor Trend Car of the Year in 2013. Our first, great award, first car. Pretty good start. Kind of a home run, I think. But that whole process resulted in a linear process that you see on the screen. We designed first, then we engineered, and then we figured out how to manufacture it.
Yeah, I think that's really important. When we were designing the car together, we didn't even know where we were going to build it. And so we came up with...
I didn't even know Lars when we were doing it.
That's true. So once we got Fremont, we were very fortunate, and we figured out the manufacturing solutions, sort of like we were flying a plane and putting the wings and building the engine at the same time. So we knew we had to do better.
Yeah, we knew we had to be better in order to scale. And as part of the master plan that you've read, Model 3 needed to be a smaller, more efficient, and more affordable version of Model S. But it had to be equally great. It had to have all the things that people loved in their Model S or Model X, but be much more affordable. And so we approached the process a little bit differently than the first time around. Now we had teams that we all worked together, so we were able to combine design, engineering, and manufacturing process all at the same time. But somewhere along the way, we changed the manufacturing process to be fully automated. And so we leaned into this whole new way of manufacturing a car, but we had already engineered it. So things didn't quite go as well as planned.
It was an amazing product, but it landed us in production hell. Many of us who lived through that carry those battle scars. It was a great idea, but it wasn't the right timing. Like Franz said, automating something that we designed to be built manually is super hard. And we have many, many failed examples of that at the Fremont factory that we ripped out. But some of them eventually still work. This is one I actually worked on with a small team of engineers. It's still running today. And some of the engineers that came by said we couldn't do it, are no longer with the company, but it's running, and it's running faster than ever. So we kind of self-imposed constraints on the design when we were doing it to be built manually, and we really didn't think about it. But despite all that, Model 3 is the best-selling EV ever.
Yeah, and Model Y, which is derived from Model 3, is about to pass that. But we knew we had to improve the process further. And with Cybertruck, we designed a vehicle around a vision that actually started with the manufacturing process. And in this case, the materials dictated the design.
Forming full hard stainless steel isn't rocket science, but it sure isn't easy. And it limited the way we could do it.
Yeah, absolutely. It really forced us to think about designing something in a way that you couldn't normally stamp panels, you couldn't form them in a traditional way. So you ended up with very linear bending processes that are just not in automotive kind of language of manufacturing today. But it actually created a very efficient process and one of the most dynamic designs ever, I believe. It's definitely something that's going to change the road landscape.
Hopefully you guys saw it down there and you experienced it. It's definitely real. Those are real trucks. We're on our way to build them. But what that stainless steel opportunity did for us, it has let us rethink the factory footprint. We don't stamp those, that's a huge part of it. We don't even paint them. So our footprint got smaller, and we started to think about innovative ways to take those constraints and make great products.
But that constraint didn't really change the end result of the truck. It's a super dynamic truck, and it has all the functionality you would expect out of any of the other competitive trucks. And the best thing about it, it's coming this year.
So ideally, after all that, we would design, engineer, manufacture, and plan for automation happening together. It gives us the opportunity to question requirements. This is something that is fundamentally only available at Tesla. In the places I used to work and the top manufacturing companies in the world, they don't sit together.
Yeah,
we are one team.
Nowhere I know has all these teams together thinking about these processes from the very beginning.
In fact, all of those engineering teams, manufacturing, design, automation, they're all in one org. They all report to one person. We can't point fingers at each other, so we have to solve them together, which is the best way to innovate. The traditional way of making a vehicle is this. You stamp it, you build a body in white, you paint it, and you do final assembly. And what's interesting is these shops are dictated by the organizational structures that exist, and they're dictated by the boundaries that exist in the factories that are laid out. If something goes wrong in final assembly, you block the whole line, and you end up with buffering in between. This is at the tail end of its manufacturing optimization. Henry Ford first invented this assembly line in 1922. It's been 100 years, and it's really hard to make a change after 100 years. And when you watch it happen, it's actually really silly to a guy like me. You take all these stamp panels, you put them together, then you put them in a framing station, you build a body that looks something like a car, you put the doors on, and then you paint them. Once you get the color, you take the doors off, and then you start putting the interior inside the car. It comes in through the openings that already exist. I wish it went in like this big piece like this, but there's actually people coming in and out of the car. There's awkward movements. Then we lift the car up, we put stuff from underneath it, we put it down, then we put the seats in the car, and finally, we close it all out with glass, and we bring those doors that went away for a trip, and we put them back in the car. Most of the time, we're doing this with a big, giant car and moving it and doing really nothing to it at all.
What's funny, though, in this kind of whole process is that just recently, Toyota just called this an engineering work of art.
True.
The Model Y.
That was humbling, but at Tesla, it's not good enough. If we're going to scale the way we want to do, we have to rethink manufacturing again. As part of the master plan, we have to make another step change in cost. We started this on Model Y when we made these huge gigacastings, and we deleted hundreds of parts. We simplified assembly with the Model Y structural battery, where we decided the floor should be a part of the car. The battery is the floor. We put the seats and the interior on the battery, and we bring it up through a big open hole, and we assemble it. And this allowed us to do things in parallel, fully rethinking the process and reducing the final assembly line by about 10%. And we thought, maybe we could do this other places.
Yeah, I mean, in a way, the constraints become part of the solution rather than a problem.
So when you think about what I'm trying to say, I really want to hammer this home. When you have a car that's about 5 meters long, and you have people working around it like we did in Model 3, and we change that to this process where we take different parts of the car, and we can do more at the same time, like we did with the Model Y structural battery pack. What you see here is us doing that on the front part of the vehicle, or the rear part of the vehicle. That means we can get more people working on the car, or robots, working on it at the same time. That means we have better operator density, less time doing nothing. I call that space-time efficiency. It has nothing to do with quantum mechanics. We can have that conversation later. But we get 44% more operator density, which means more work, less time walking back to the station, 30% improvement in space-time efficiency. And because we're not building it in and out of the car with those slow movements of those robots I showed you from production hell, when we go to automate it, it's going to be a lot easier. In the end, that will probably look something like this, where we balance parallel and series manufacturing in a way where we only do things that are necessary, with a much shorter final line, blocking a lot less of the entire rest of the factory, so we can optimize material flow using the best practices. And what that means, it's going to look something like this, where we build all the sides of the cars independently. We only paint what we need to, and then we assemble the parts of the car once and only once. We put them where they need to go. The interior is attached from a bottom-up or a top-down strategy, so there's more access for those robots and people. We aren't moving heavy objects around and doing nothing to it, and it means we're doing more work on the car more of the time. And then, when we take all of these tested sub-assemblies and we put them together, we finally assemble the car only one time, putting the sides on with all of their parts to a front and rear that was already assembled, carrying the floor in with the seats, and finally boxing it out with the doors one time, just like Cybertruck. So in the end, you get the same car, but it's not going to be a Model Y.
Yeah, this is not. Yeah. This is a Model Y for illustration, not the next-gen vehicle.
In the end, what does that mean? To increase the scale and adoption of electric vehicles on the orders of magnitude that we just showed you, we have to make constraints part of the solution. It leads us to greater than 40% reduction in footprint, which means we can build factories faster, with less CapEx and more output per unit. Faster, less CapEx, more output per unit dollar. Zach's going to go into more details on this later, but it also means through this innovation and some of what my other engineering colleagues are going to talk to you about in the future, we'll reduce costs as much as 50%. This is the 2-for-1 concept you hear me and Elon talking about on earnings calls.
Yeah, so I think our track record proves that we can deliver the best cars, and we deliver the best cars in spite of, because of these constraints. And I'd love to really show you what I mean and unveil the next-gen car. But you're going to have to trust me on that until a later date. And I promise we'll always be delivering exciting, compelling, and desirable vehicles, like as we always have.
Have we ever not? We
Yeah.
always do.
But what else is Tesla known for?
Speed. So with that, I want to bring on Colin, who's in charge of making our cars go fast.